much. Thank you.
Thank you. Okay, welcome to the last lecture. Today I'll talk about bit rings. The idea of the bit ring is based on following bit decomposition.
Is it amazing? Sorry. Is it amazing? It's on the sideboard.
Oh. Okay. So you recall any quadratic form Q decomposes as an orthogonal sum of three quadratic forms for well-defined type. There's the totally isotropic, and there is a hyperbolic part, and there is an anisotropic part. So totally, this part is in fact the radical of the associated bilinear form. Particularly, the form is completely zero on this space. This is an hyperbolic space. It's isomorphic to some hyperbolic space associated to some vector space, and isotropic. This means if you have a non-zero V, then it follows that zero V is not zero. And this decomposition is not unique as decomposition of subspaces, but the dimension of this decomposition are unique. And so the idea is to say, first of all, we should not consider something which has a radical. The sum of these remaining two are actually regular quadratic forms. And so we just concentrate on regular quadratic forms. And later on, we will see that we will even throw away the hyperbolic part, because in a sense, if you have a hyperbolic form, it is boring. It's just determined, just given by a vector space and so on. Not so much. Okay. But we will start with looking at symmetry classes of regular quadratic forms. And I will use the notation W hat plus of F, a notation which will become clear only later on. These are, but this is a set of all regular quadratic forms. And this is the isometric. For everything which is isometric, Q is put into this class. Now, we have learned in the course that there are two structures which we can define on the set. Namely, this has an addition. Right? Because we can add, we can define plus by saying the class of Q1 plus the class of Q2 should be the class of Q1 per Q2. Of course, what I use here is that this is well defined, this is independent of the isometry classes. Okay. And now this addition has the following properties. First of all, it's commutative, right? This is also the same as Q2 plus 1. It has a 0. And if I take the zero quadratic form, meaning the vector space on which we have the quadratic form length is the zero vector space. Right? Then I take Q2, and then of course I get Q2. It's associative. Same as taking Q1 plus Q2. Okay. So it is nearly a group instead, except what is missing is there's no inverse, but it satisfies a rule which is similar to being an inverse, namely bit cancellation. This means the following. If we know that Q plus Q1 is the same as Q plus Q2, then this implies that Q1 is isometric to Q2. So this is called bit cancellation. This is a fundamental result which is used over and over again. It's very simple. Now, the set also has multiplication. Right? We can define Q1 times Q2 as the tensor product Q1, Q2. And multiplication has similar properties as addition. Right? So the structure with respect to plus, which I have recalled here, this is called a commutative semigroup. Commutative semigroup with cancellation. Now, this is also a commutative semigroup. Namely, yes, I've stated last time that Q1 times Q2 tensor product 2, this is commutative, it's associative. So we have another commutative semigroup. And now we can link the two operations by distributivity. Right, so Q1 times Q2 plus Q3 is the same as Q1 times Q2 plus Q1 times Q3. Okay, so what did we have? What did we got? We have a commutative semigroup with respect to addition. We have a commutative semigroup with respect to multiplication, and the two are linked by distributivity. And you may have heard how one calls such a structure. This is called a commutative semiring. Okay. Now, you all know another example of a commutative semiring, namely natural numbers. Add, multiply, what the status in the natural numbers, and I also have cancellation. Okay. Now, you know the natural numbers are embedded integers. This is a construction which one can generalize. In fact, works for any commutative semi-ring and has special properties if we have isolation. And this is called the Grothendieck construction. Okay. Namely, like for the natural numbers which are embedded in the integers, which are real good ring, the ring to consider, we will now embed general construction, which will embed our commutative semi-ring into a ring. Namely, the theorem says there exists construction unique bona fide ring, which is denoted W hat F, called the bit Grothendieck ring, which has the following two properties. Okay. Now, a commutative semi-ring is something which has weaker conditions as a ring. So that means that any ring will also be a commutative semi-ring. So I can speak of maps going from the commutative semi-ring into a ring, which are semi-ring homomorphisms. So this big Grothendieck ring has the following two properties. Number one, my set of isometric classes of regular quadratic forms, if this embeds into the bit Grothendieck. And it's not just an embedding of sets, but it's an embedding of inclusions. It's a homomorphism of semi-rings. So that means multiplication and addition is induced by the multiplication which we have on this semi-ring. And number two, it is universal in the following respect. Namely, if I if R is a ring and phi is a map that we had plus to our ring R, ring now. This should be semi-ring homomorphism. R is a ring, so I can do that. Semi-ring homomorphism. Then there exists a unique extension to the bit Grothendieck ring. So this means the following. Here we have our semi ring. Here we have our map phi R. Here we have the inclusion into the Grothendieck ring. Then this phi gives rise. And this is a map of rings. Right? So this indicates also, if you want to prove something about this with Grothendieck ring, what you have to do is you have to find semi-ring homomorphisms from the W plus N, then I will use it. Okay. Now, this ring is constructed by using a certain equivalence relation on the direct product of W hat. So I will just give you, I can view the elements. So the element of W hat of F, they are formal differences. Like negative number is a difference of two natural numbers, right? So they are Q1 minus Q2. Now, you can have two different natural numbers which represent the same negative number, and so we need to say when are two differences the same. Right? So I will say Q1 minus Q2 is the same as Q1 prime minus Q3 prime if and only if there exists a regular quadratic form filled such that, well, you can bring this to the other side. It's 3 or 2. Yeah, 2. Such that Q1, as long as if you bring the Q2 prime to the other side, it becomes a subset by a some this would be isometric to prime solving some two. Now, how do you add string? Well, how you the same way as you would add differences of natural numbers. Multiplication the same way. But let me add for introduce something. So an element in this Witt-Groton ring is of the form Q1 minus Q2. However, if you look at this description of then I can add any good order. We'll add minus 2. Add 1, minus, and I have 2. Okay. Now, Q2 of someone assigned to minus Q2, this is a hyperbolic space. Okay. And this is any vector. This is a vector. Okay. Yes. So this means that I can write any element in my Witt-Groton ring very special way. It is actually just written as a set. This is the same as taking any vector form plus n times I'll write it down and explain it. Okay. Now, in the Witt-Groton ring, we look at hyperbolic forms. Right? So we have the following. Look at the hyperbolic form. then this decomposes, right? This is as a quadratic form. The vector space is not so important. It's isometric to H times at the n. N is the dimension E. And now, one of the homework problems is that you have here a direct sum, and this goes out. This is just H, normal sum is H, or H, so N vector, and H is an abbreviation of H dot N. Right, so this is the hyperbolic plane. Dimension 2. Okay. Now, one can multiply any element, regular form, multiples a quadratic space. What you get is, if you look at the Q tensor product H of W, and this is isometric to H of the tensor stuff. So what this says, this formula, is that if in the Witt-Grothendieck ring multiply any quadratic form, so hyperbolic form, to stay within the set of hyperbolic forms. So this says that if I look at the ideal generated by H, it's just n times H. H of W. Then this is an ideal that we've got.
I'm missing one here now. If I have a diagonal form on two-dimensional vector space with x and minus x on the diagonal, why is it equivalent isometric to one with one on the one minus one on the or four on the sum? So it's necessary for Q2 minus or form minus Q2 is hyperbolic. Why is that?
Right, you should do the exercise.
I see. I'm doing my head.
That's correct. Take reflection. Good.
It's the identity your ring that you had.
Sure. Identity is the identity. Or, okay. I write it out. Get it? One. Just the isometric classes of the form given by one. So you remember one was the form from F to F, and that's X to X. As you can see, if I found good. This is one, then the canonical isomorphism of the vector spaces from F tends to B to B is in fact an isomorphism. Okay, so now we have an ideal. So you can guess what I will do, what we will do. Plot it out. So I take Witt-Grothendieck ring, plot out the ideal generated by the class of the hyperbolic plane, I get a new ring, which will be denoted W of F. This is pretty. Okay. Now, there's a set. Right. As a set, if you look at this description of the Minicourse, that just symmetry classes of quadratic forms and no longer different. We add multiple forms. Okay. Now we have more than our this. So what is left are just. So the grid ring itself is no longer the element, are no longer differences of quadratic forms. They are just quadratic forms. Q is a rectangle. Right. There is, of course, a sort of notational abuse. Namely, I use the same notation for isometry classes in W hat plus, in W hat, and in W of F. So that's the okay. Now, the width decomposition said that any regular quadratic form is hyperbolic time plus something anisotropic. Now, this means I can write this as isometry classes of hyperbolic plus something anisotropic. But in the width ring, hyperbolics are 0. So this is not the same as the isometry classes. Prime is anisotropic. Okay, I mentioned that everything hyperbolic by definition is 0. So the 0 in the mid range is just a 0 form, or anything which is an integer multiple of h. What are the negatives? So this is, it has plus and multiplication. Multiplication is induced from the multiplication of the Grothendieck ring. Now we know what is a 0. So the negative of Q is a very nice description. It's just minus. Okay. So where minus Q was defined as follows. So if Q goes from B to F, then minus Q goes from B to F, that's B to minus. Now, why is this true? Right. So since, well, if I add Q and the isometry class of minus, right? So this is the isometry class Q per minus Q. Well, this is hyperbolic. So this is 0. So this equation tells you that the negative of minus goes in. Okay. So now what we have defined for any field, start with, we have defined the bit range of the field. And of course, now you want to know, well, what is it? Right? Because this description by taking differences of regular quadratic forms, or even this description in, well, an abstract way, this is somewhat complicated. So I will give you two examples. Of the structure of the bit ring for concrete fields. But first, remember that we're working over field of characteristic not two, and this is now really necessary. That does not exist, by the way, a bit ring in characteristic two. There only exists a bit group. So we have seen that any quadratic form, regular quadratic form, can be diagonalized. So if Q is regular, we know that Q can be written as a direct sum, as a sum of A1 up to An. Where AI are non-zero scalars, and we have abbreviated this as A1. Regular by its equivalent, but these AI are non-zero scalars. Now, we have also seen, I think, if you look at the one-dimensional form, this is isometric. A is isometric to B, if and only if A times squared the class of if and only if A divided by B is the square. Squared. And so I can, in each of these components, I can change my A by a B if A and B lie in the same square. So A1 up to An is isometric B1 up to Bn if AI square same as PR, where square class is just we squared new life in X times, which is F minus 0. Okay. However, clearly this will not give me all isometries between these two forms, but at least it's a start. Okay. So now let's look at, after this general discussion, let's look at the first example. Then we suppose that we are in the lucky situation that everything in F is a square. So suppose F times is F times squared. Okay. Well, I take my regular quadratic form, I diagonalize it, I got scalars, I use this line here, can with can change all the non-zero scalars to say 1. So then I know Q is isometric to 1. So then follows that in this, well, I should say this. These fields are called quadratically closed, but anything which is algebraically closed also satisfies this, particular satisfies this condition. So I should have written here G F is algebraic. Right, but there exists a field where this condition holds, which are not algebraic. So what this means is that the isometry class Q is just n times the isometry class 1, which is 1. This is just n times. So this is n times plus 1. The n is, of course, the n is the dimension. Okay. Now, this implies this then follows that the Victropendic ring, in this case, is isomorphic to the integers, and the bit ring which we get by modding out hyperbolic spaces, well, you look at the dimension formula of the hyperbolic space, it's always an even number. It's not so easy, not so difficult to show that the bit ring itself is just very simple. It's two sets. Okay. Example B. Well, let's take out the numbers. In fact, the same works for any input. Now recall that f dq is positive respectively negative respectively. If q of v is positive, every respectively is negative for all possibility. And I'm sure you have heard about the inertia theorem of Jacobi Lester, which says the following. Well, given a regular form of real numbers. There exists a decomposition of B. He decomposes that plus minus minus such that Q restricted plus minus positive respectively negative. And this decomposition, while not unique in the level of vector spaces, is unique at the level of dimension. And dimension B plus minus. So, you may have even seen this in the course. Now, let me give you a proof not due to Jacobi Sylvester, because Jacobi and Sylvester were mathematicians in the 19th century. But I will now use result on bit decomposition. So I will give you a proof, great proof for it using it. Okay. Well, any quadratic form can be diagonalized as we have said before. So I reduce from an arbitrary form to a diagonal form. And I can permute my basis element such that first get some only positive numbers, then I have negative. So this means now squares in the real order. So I can every positive real number is 1 times the square. So I can reduce the positive numbers 1, negative numbers to minus. So this is isometric to a certain number of ones, then a certain number of minus. Okay. And so I declare this as my B plus, and space spanned by the corresponding basis element corresponding to -1. This is y by B minus. So the form is positive definite here. It's negative definite. Okay. So this takes care. It's the first part. AV decomposes as something where the form is positive definite, something where the form is negative. Now, the inertial theorem says something more. It says the dimensions are unique positive space. Now, what I do then? The following. So that D plus minus is the dimension of D plus minus. Now, for simplicity, for easier notation, suppose that D plus is equal more ones than I have minus. Now I commute by basis elements so that 1 and -1 can alternate. So then the Q is isometric to have 1, -1, 1, -1. And then from some point on, because I assume that because it's minus, I have just 1. Now this is a diagonal form, so in fact I can write this in this form, make a plus sign and sum here. Even more, I can write 1 minus 1, orthogonal 1 minus 1. Now, any form 1 diagonal has 1 minus 1 on the diagonal is hyperbolic. Right. So this form is hyperbolic. The form which has only 1 on the diagonal, well, it's positive definite, but in particular it is subtractive. Right? So what I have written there is then just a difficult. We have decomposed our quadratic form of the real thing. This is hyperbolic, orthogonal sum to something which is isotropic. Now, the width decomposition has as a second part that dimension unique. Now, what is the dimension of the hyperbolic? Well, it's exactly the number of minus ones. So the dimension of the hyperbolic part is this times 2. That's 2. This. And the dimension of the anisotropic part is E plus minus E. And these are unique. Right? And it's easily seen that this implies E plus minus. So, therefore, what I have is that any quadratic form with reals follows statement of the Jacobi-Silvestri theorem. Now, end of. Now, consider a set of isometry classes of regular quadratic forms of fields. Then I can define a map into the integers. And it sends to dimension plus minus dimension minus. So the inertial theorem says that this map is well defined as a map. Because the dimension of the plus and the dimension of the minus is independent of each other. But it's easily seen that this map is actually a homomorphism of semurings. Okay, so remember the universal property we probably being once any homomorphism of semiring extends. Right, so I get a ring homomorphism. Which is given now. We had hyperbolic plane. Hyperbolic plane. This is just one minus one. So b plus is 1 dimension, minus is 1 dimension. This is 0. So because this is a ring homomorphism, vanishes on the ideal for hyperbolic spaces. So that means descends to a map D from the mid group of R onto integers. And in fact, it's easily seen that this is an isomorphism. Okay. So the mid group of the integers is in fact just isomorphic. Sorry, mid group of R is isomorphic to the integers, and the total mid group is an extension, certain extension of. Okay. Now, end of this example. So, I have given you some examples of width group. There are many more fields where I know precisely what is the width group of, let's say, a finite field. So a finite field is always ring is always it's always order 4, and one knows what are for periodic fields, one knows for the rationals, for example. It's an infinite group. One of the example exercises is gives you some hint how to prove that this is an infinite set. Okay. So, of course, at one point we run out of interesting examples of fields. And so one asks, okay, is there some general structure? Does there exist a general structure for width groups? But what can one say for width groups in general, width rings in general, without specifying the field? So I will tell you a little bit about what I'm going to check. Yeah. And the story starts with giving you an unsustainably ring homomorphism. So F is now arbitrary. Of course, the characteristic of F is true. Now, for the big ring of the real numbers, we have used this particular dimension homomorphism, but we can just map everything on the dimension of the underlying vector space. So what we do is consider W hat plus for F, and we have a map into the integers, and regular quadratic form VQ is mapped simply on the dimension. Okay. Now, this makes sense because this map respects the isometry classes. Right? So if you have isometric regular quadratic forms, they have the same dimension. And also it respects plus and addition and multiplication. Right? So the dimension of a tensor product is just the product of the dimension. Okay? So in other words, this is the semi-ring homomorphism, and therefore by the universal property of the Witt-Grothendieck ring, I now get a ring homomorphism which goes features. This now is a ring homomorphism. So let's call this yes. Call this at ring homomorphism. Okay, so what does it do? Well, if we write the elements of the Witt-Grothendieck ring as differences, and it just U2 just maps this as a dimension of 1 minus the dimension V2.
This is not the same as you did for.
Oh,
Sure. It's a plus there.
okay. Well, that's good.
It's the trace.
Huh?
Trace is dimension.
Wow. Good. Okay. Right. Well, it's a ring homomorphism. What do? We look at the kernel, of course. The kernel will be an ideal. So, yeah. That the kernel yeah. So, these are all the differences where the V1 and the V2 have the same dimension. Now, what does he have to the class? Well, the class of H has some two dimensions, so this is 2. So he had perhaps my ideal generated by H. Who's that? So now what is our situation? Well, situation is as follows. We get a huge diagram. So we have double that middle. We go deeply, and we go, or we have integers, and every integer rises in this form. And we have defined the ideal, which is the kernel of. So we get an exact sequence. Now, we also have the bit ring, which is a quotient. And what is this quotient by the ideal generated by the hyperbolic plane? Then okay. Now, this is mapped, see, so this is mapped onto that. Now, this diagram can be repeated. There exists a map B here, so that this becomes commutative, and it has a kernel. So, by definition, I use French. It's just this the set of, say, regular nice forms. Such that this E Q is set. Okay. Of course, this. So this is the situation. Right. Now the I has then it's got the fundamental. So now the idea, starting in the 60s, where this was known, was study now the bit ring of an arbitrary field F by looking what happens to I and what happens quotients of I by I squared, etc. So let me recall product of ideals. So if I and J are ideals in some ring, like say R, then I can define what is the product of I and J. I times J. Well, we say the ideal generated by the actual products, but this is not an ideal. So I have that sums, let's say L10, L, J, L, I, L, I, the N variable. So this gadget becomes a new ideal. So this is an ideal.
It's general construction for any of them.
So what we can do then is to say, define forms. Okay. Namely, we have the width ring of our field F, and it has as an ideal, fundamental ideal R. But I can take J equal to I in this definition, and so look at the square. And define I squared, which by definition is just I times I. So this is not the same as taking squares, the element. This is defined as 4, and this will be here. And I can continue. I get a cubed, which is I times squared, continue, I got IN, I continue, so on. And there is no theorem which will tell you that this actually stops. Okay. So, principal idea now, the study of the bit ring was that we study this by approximating the ring by looking at quotients here. Consider n modulo I plus 1. What can you say about these quotients? Now, of course, from the point of view of multiplication, you lose none, because multiplication here, the induced multiplication is trivial, but we now concentrate, plus we concentrate at the B improved function. Now I'll give you a couple of results about this quotient. Well, first of all, IN itself is span only and by a very specific product, namely it's spanned by forms which are at this point. So this is a two-dimensional form. I can take its multiplication by another two-dimensional form. And I take n factors. So here I use multiplication, but in fact what it is, this is simply the class of one tensor product of the corresponding form. Now, these quadratic forms are very special. They have marvelous properties. They have a special name. They are called crystal forms. For anything which is arithmetic to product, tensor product, this is a piston. Okay. Now, suppose that I n modulo I n plus 1 is always a given group of exponent 2. And one knows, at least in this like early 60s and 70s, one knew the first couple of quotients. Right? I mean, we know already W modulo the ideal. This is also exactly 2. So that's the first one. Now, let's know something about I. So the next quotient would be I modulo I squared. So you can show that this is isomorphic, taking one invertible elements of F modulo squared. And it exists a map in this form. It's given by the determinant brand Schmidt matrix associated with brand. Okay. Now, fine. There are now infinitely many research problems, right? What is IN modulo I plus 1? But let me just give you one more. So anyway, one knows what is the next quotient. What is in the sense that what we improves. So this is this spectacular result in the movement published with Jonas, who said, find K2 of that as follows. So this is just look at F times S is equal. Factor out span E like that. A plus B. Now you can define a map from FR to I2 modulo extend A comma B to what I do is this I take 4 1 comma A tensor product 1 comma B. Then I take this class free. The problem is that this is another map. Then I go, its kernel, and this includes a group of avoidance of from K2 of F, want to go into a squared onto I2. Now, of course, Miller was also interested in what happens next. So, made a couple of conjectures, so-called Miller conjectures, and they were remarkable in the sense that they combine a general form of K2, so-called K theory, and We combine this with the direct sum of IN, and map this to the direct sum IN squared. There was another map group homology, Galois, which is for a different thing. So this is Galois. Right? There, in fact, one could prove that there exist maps, that this becomes a diagram. And nobody knew how to prove this actually until and he proved that these maps, which were defined by Miller, these maps are all isomorphic. He proved this by using the most complicated mathematics available. This was 1998, motility homology, and so on. And he got the Fieldsman. And so he got the Fieldsman for his proof in 2002. So what you have to do in order to get the position somewhere, just find an easy proof. Thank you very much. Question?
Question. Thank you, Erhard, for the wonderful Minicourse.
Yes, these wit groups, these wit rings. I've seen some examples, and then it's just a complicated way to study them, but is there like an inverse problem? Like an inverse Galois, when you try and make specific Galois groups, can you make specific wit rings? Right, starting with you.
Meaning every bit ring, Galois.
Is every ring a wit ring?
Every clear.
Yeah, the real one, but actually.
It's likely because of the there's equivalence problem. Because so the Galois homology here is related to torsion in the problem. There is a theorem saying that every problem. But there's no explicit.
Yeah, I guess every group is a brother. I mean, you have to have this group, which we can send to that's.
But look, I'm not, I cannot answer.
Yeah, I'm just wondering if there. But for like a field of characteristic, not to can't be a wit ring.
Can he?
Like the real numbers cannot be a wit ring.
Oh, no, but you're looking at the Galois.
No, I just want like the wit ring is for which ring is going to occur.
No. So the answer is I don't know, but I thought that there is an abstract characterization of which rings are which rings. But it's an interesting question. I mean, particularly, we give you a strange ring, and then if you have a concrete construction of the field, it has this as a bit ring, yeah.
For fields of characteristics to other some theory like related with rings, anomalous constructions.
Yeah, so for So let's go back to the definition of the weak ring limit. The multiplication is the tensor product of two quadratic forms. Tensor product of quadratic forms in characteristic 2 does not make sense. There is no tensor product. So instead of the weak ring, you get a weak group.
Just consider
And
addition.
so there is a theory there for weak rings in characteristic 2, and there is also corresponding a conjecture. This is so-called Bloch-Kato conjecture, and as it turned out, surprisingly, the proof of the Bloch-Kato conjecture was in characteristic 2 was much easier than the proof of the Miller conjecture. Not doing. This was Bloch-Kato was proven in the 80s. This was proven. But there's still, it's a very complicated proof, and it, you see, usually the Fields methods are only given for published works. Had to be published. However, not in this. It took ages to publish actually all the details.
But what's the only did it in characteristic not to?
Yeah.
So you should have got a sum field medal.
Well, on what he got entered. Well, I mean, he got a Fields method, but they made an exception. Exception for the rules. By the way, does everybody know here what's the Fields method? So the Fields medal in one sentence is sort of the equivalent of the Nobel Prize. There does not exist a Nobel Prize in mathematics, and so the equivalent is the Fields medal. It is given out every 4 years at the ICN, the International Congress of Mathematicians, and it's the most, besides the Arbor Prize, it's the most prestigious award which you can get. And I mean, you can list, you go to Wikipedia and you can see who actually won a Fields medal, and it will be clear to you then, yes, these are among the best